This is 1.3. We are going to be looking at properties of limits and then how we can find limits analytically. So far what we've looked at is an introduction to limits and what they mean and how we can find them using a graph and a table. There are other properties of limits, so you are going to want to take a look at the notes and familiarize yourselves with these properties. These properties are all embedded in our examples that we'll go through today. So you will see some of these like a scalar multiple, a sum or difference, product quotient, and power. You will see all of those. These properties are just embedded as we go. So just make sure you take a look at them and see if you can kind of understand what they mean. Limit of a composite function is another one that will come in handy, especially as you go through and do AP classroom assignments. The limit of a composite function f of g of x as x approaches c is f of the limit as x approaches c of g of x. So what you want to do is find the limit as x approaches c of the inside function first, and then take that value and put that into the f function, the outside function. So all of those properties make sure you are familiar with. All right, so some strategies for finding limits analytically. First, what you're always going to want to try and do is see if you can just use direct substitution. So the value that you're approaching, that C value, try and just substitute it in. If that doesn't work, so for example, if you have a rational function and you substitute that value in and get 0 on the bottom of that rational function, you can try and factor the top and or the bottom and then cancel out any terms that would make a whole or anything that you can factor out or cancel out. If you have any radicals, you can try and rationalize the numerator or denominator, depending on where those radicals are. So if you can't factor and cancel, then you can always try and rationalize if you have radicals in there. Another strategy you can try is if it's trig, you can try and use different trigonometric properties as well. All right, so let's take a look here. First thing you always want to try and do is probably just directly substitute and just double check and make sure that doesn't work first. So for this first one, the limit of x squared minus square root of x as x approaches 4, we're just going to try and substitute it in. So 4 squared minus square root of 4 equals 16 minus 2, which is 14. All right, so that ended up working out. It was all good. Number 2, we're going to try and directly substitute. If we directly substitute with this one, we end up getting a 0 on the bottom. 2 minus 2 is 0 since we're approaching that x value of 2. So what we're going to do here is we are going to try and factor out this top quadratic and see if we can cancel out an x minus 2. Now, as you show your work with limits, one very important thing, and this is an important thing to remember, especially as you go and we start preparing for your AP tests that you'll have this spring, you want to carry this limit notation through until you get to the direct substitution part. So we're always going to start by rewriting the limit notation. Now we're going to do the factoring. So x squared plus 2x minus 8 is going to be x plus 4 times x minus 2 all over x minus 2. We can see that that cancels out. So this is just the limit as x approaches 2 of x plus 4. Now we can try and do our direct substitution. 2 plus 4 equals 6. So the limit as x approaches 2 of this function is equal to 6. And you can always try and graph these and just check that value and make sure it checks out. All right, number 3. Try direct substitution. If we put 0 in, we get 0 on the bottom. There's radicals, so we can't really factor and cancel. So what we're going to be looking at doing here is rationalizing. And on this one, we're going to rationalize our numerator. Sometimes you might have to rationalize the denominator. It just depends on where the radicals are. So in order to do that, you're going to multiply your function by the conjugate of the top. So square root of x plus 3 plus square root of 3. Remember, the conjugate is basically just changing that middle operator from a minus to a plus or vice versa. And we have to make sure we do that to the top and the bottom. Multiply by square root of x plus 3 plus root 3. All right, now we're going to do some distributing here. So again, carry that limit notation through. We're doing the limit as x approaches 0. We distribute here. We get x plus 3, and then we get root 3 times square root x plus 3 minus root 3 square root x plus 3. So the reason we multiply by the conjugate is because you can cancel out that term then that would be in the middle. So we're just going to skip to the last terms here. Negative root 3 times a positive root 3 is a negative 3. All right, and then on the bottom we have x times root x plus 3 plus root 3. All right, and you'll see in a minute here why I didn't distribute that x through. So if we simplify this a little further, our limit, the top, this plus 3 and minus 3 becomes 0. So on the top we have x, and on the bottom we have x times root x plus 3 plus root 3. Well, and look at that. These x's end up canceling. So we just have the limit as x goes to 0 of 1 over root x plus 3 plus root 3. And then now we're going to try and do our direct substitution. So this is equal to 1 over root 0 plus 3 plus root 3, which is 1 over root 3 plus root 3, so 1 over 2 root 3. All right, so using rationalization, we got the limit as x approaches 0 of this function to be 1 over 2 times root 3. All right, another strategy we can use is finding some common denominators, just trying to manipulate it algebraically. It's going to be kind of similar to what we just did with rationalizing the denominator. And this one has a few different variations on it. Like you could really do this multiple different ways. This is just one way that I'm going to do it that I'm going to show you how. And maybe mine's the long way. Maybe you have a shorter way of doing it. As long as you find a way that works for you, that's great. All right, so the limit as x goes to 0, we have to use some other type of strategy because we can't have a 0 on the bottom if we directly substitute. So I'm going to look at this one as this top fraction here, I'm going to try and combine and make into 1. So what's going to happen is to find the greatest common denominator, I'm going to multiply this fraction by 2 over 2 so that I can, match that 2 that's over here, and then multiply this one by x minus 2 over x minus 2. Okay, so when I do that, I get 2 plus x minus 2 over 2 times x minus 2. And since this was over x, I'm just going to say we multiply that by 1 over x. Instead of leaving it as like a fraction within a fraction, just multiply by the reciprocal right away. So the limit as x goes to 0. Here we have 2 minus 2, so that becomes 0. So here we're just left with x on the top over 2 times this x times x minus 2, like so. All right, I see some more simplifying that we can do. These x's cancel, so we're left with 1 over 2 times x minus 2. So now we can try and do our direct substitution. So I get 1 over 2 times 0 minus 2, which ends up being 1 over negative 4, so negative 1/4, like so. All right, so there's some basic just algebraic ways that you can solve these. Last thing we're going to look at is, this is kind of just a preview of what's going to be coming up when we get to chapter 2. I know we just started chapter 1, but it's good to know because we are going to be using these specific limits later on. So we're going to be looking at the difference quotient here on this one. And if you, we're going to look at the difference quotient. And if you remember, our difference quotient was just this function right here, f of x plus h minus f of x all over h. And what we do is we take a function and plug in the x plus h, subtract the original function, and divide it by h. We're going to add a step now of finding the limit as that h value goes to 0. Now this does have a specific purpose in calculus. We're not going to worry about that right now. I just wanted to give you an introduction since this is an analytical way that we're going to have to solve limits coming up here in the future. So first we need to take this f of x and put it into this difference quotient here. So without doing anything with the limit for now, I'm just going to get that difference quotient set up. So f of x plus h is going to be our function where all of the x's are replaced with x plus h. So x plus h squared minus 2 times x plus h plus 1. And I like to simplify that first. So x plus h times x plus h is x squared plus 2xh plus h squared minus 2x minus 2h plus 1. And then I think that's all we can do with that. All right, then from there we have to subtract f of x. So our f of x plus h minus f of x. F of x is x squared minus 2x plus 1. Let's subtract that then. So we are given, let's see here, x squared minus x squared, negative 2x minus a negative 2x, and then 1 minus 1. So we're left with 2xh plus h squared minus 2h, and that looks like it. Okay. All right, then your next step is to put that all over h. So if I divide all of that by h, you notice each of our terms on the top has an h. So we can factor out an h. And divide that and cancel it out. So our function right here, the f of x plus h minus f of x over h is 2x plus h minus 2. Okay, but we want the limit as h goes to 0 of that. We actually want this, the limit as h goes to 0. So since I already did all the simplifying, the limit as h goes to 0 of 2x plus h minus 2, I can just plug h in for, or 0 in for h, and just do my direct substitution. So I just end up with 2x minus 2. And yes, it is normal to get an expression there. This is actually an expression that represents slope at a point. Okay, and we will come back to that, but it's just a little preview of some calculus we have coming up. All right, so go ahead and practice this first part, these algebraic limits, and then come on back for the second half of 1.3 notes.